In this video, I will demonstrate the DGEPSA problem-solving process using our Kinematics problem-solving template. Let's say that we're given a car traveling at a speed of 10 meters per second, which accelerates at a rate of 2 meters per second squared over a distance of 30 meters, and we're asked to find the time it took the car to travel this distance. I'm going to show you how we'll break this problem down and go through each step of the problem-solving process. The first step is always to represent our object using a pictorial representation. That means a sketch and a coordinate axis, and you should include symbols in your sketch. So I'll go ahead and in my coordinate axis here, I will say that up is going to be positive and right is positive as well. This is how I define my directions and communicate them to my audience. So I'll go ahead and check that I did that. I'll go ahead and draw a sketch. So I have my initial state here. The car is traveling with some initial velocity. Again, I can draw an arrow because velocity is a vector here. And I'll say that V initial is 10 meters per second. And I've established that this car is traveling to the right, so that's a positive velocity, and that's my decision. Then I'll say the final state here, the car has accelerated, right? And we're given the rate of its acceleration. So I know that it's going to be faster than it was before. I don't know the final velocity here, though. I don't know that. I do know that the distance from the front of the car, essentially, beginning and end, is 30 meters. So that's my distance, or in this case, displacement. Because we're only traveling in one direction, distance, displacement, speed, and velocity will be essentially the same thing. And I don't know the time it takes between the initial and final states, right? I'm not given that information. I am given, though, that the acceleration here is 2 meters per second squared, and that's a constant value, okay? So let's see, I've done my sketch, and I have symbols for the unknown quantities. And on the right over here, I'm going to go ahead and list that. My acceleration is 2 meters per second squared. My initial velocity was 10 meters per second, and my displacement, my delta x, was 30 meters. Now, what am I solving for in this problem? I don't know the final velocity or the time, but in this case, I am asked for the time. So I'll go ahead and just choose the time here. I don't know the time. Now, I may need to solve for the final velocity to get to time, but that's not what I'm asked for in the problem. So I want to keep track of what I'm being asked for. All right, the next step in DGEPSA, we're still at the D here. We've gone through D and G, essentially. Diagram, and you're given information. The second part, this physical representation, is essentially still part of our diagramming step. In the form of kinematics, we're going to do motion graphs. When we get to forces later, this will be free body diagrams and other kinds of physical representations. But for now, just the 3 motion graphs we're familiar with. So if this car is accelerating at a constant rate, what will its position time graph look like? And I'm not going to worry about exact numerical values, just the shape, the overall general shape of the graph. Well, it'll look something like this, right? Some sort of quadratic with a positively increasing slope in this case. What will my velocity time graph look like? Well, I'll have some non-zero starting velocity, right? I'm told that the car is already traveling at a speed of 10 meters per second, so I can actually put that on here. Again, you don't have to, but if you're given the information, why not label it, right? And then I end at some final velocity that I don't really know. I do know this graph will be linear, right? It'll have a positive linear relationship, and we know that from our earlier examination of the kinematic equations and motion graphs. Then when it comes to the acceleration time graph, I know that that's actually just a straight line, and that's going to be a constant at 2 meters per second squared. So I actually can label that as well. Great, so I have some sort of idea of what I'm looking for. I don't have essentially the time, which is this point right here, right? This is what I'm solving for. So this is my time in question. One of the reasons we do these motion graphs as well, and you'll see a lot of examples in this unit, is that if you know that the displacement is the area under the velocity time graph, so I can show that I'll draw a dashed line here. This is essentially our displacement, right? So this region represents delta x. That might help you actually find time graphically. So you can actually use the graph to find an answer, or you can use the equations, which we'll do in this example. Now, the third step here is to find our relevant equations and then plan our solution. The equations you'll need are listed here. I'm going to go through and look at each one and see if I can solve for what I'm looking for, time, given everything else I have. And so I look at this first equation and I see here, well, I see that I'm looking for time, so I need to know everything else, right? Do I know delta x? Yes, I do. Do I know initial velocity? I do. Do I know the acceleration? I do. So I can actually use this equation just as it is, plug in, and then I would have to use the quadratic equation to solve for t because I would have a function of t squared. So maybe not my first choice. We'll see if we can use anything else actually. Let's see here. Do I know final velocity? No, I don't. That's an unknown. Do I know initial velocity? I do. I know my acceleration and I know my delta x. So this equation won't help me get time, but I could solve for VF, my final velocity, using this equation. And then how about this last equation? I'm looking for time. Okay, I don't know VF, but I do know VI and I do know A. So what I see now are two separate problem-solving approaches. I'll go ahead and list them right here, right? This is, we'll say, approach number 1, and this could be approach number 2. And you can choose either one, really, that you want to. Approach number 1 would be to use, and I'm going to just abbreviate equation 1 with the 1. Equation 1 to solve using quadratic equation, right? And if you need a refresher on the quadratic equation, please come talk to me and I'd be happy to walk you through that. The second approach would actually be to use equation 2 to solve for VF, right? And then once we have the final velocity, we can use equation 3 to solve for time. Do you see that? So if I use equation 2 to get VF, I can then take that, plug it in here, and then I'll only have one unknown, which will be time. So I don't have to use the quadratic equation if I don't want to, and you may not want to either. I'm actually going to use that approach. So my next step here will be to go ahead and do the mathematical representation. So actually setting up your equations, waiting until the very end to plug things in, and evaluate in your calculator. So I'll say, again, I'll use equation 2 here, that VF squared is equal to initial velocity squared plus 2 times acceleration times the displacement. That means that my final velocity is just going to be the square root of all of this already. And that means that would be the square root of my initial velocity. In this case, I was given was 10, right, meters per second. I'll show that there. Squared plus 2 times 3 meters per second squared times my displacement of 30 meters. And if I were to put that into my calculator, I would get a final velocity of 16.73 meters per second. Now, if I go on and use this in further calculations, I'm not going to want to round this. I'm going to want to keep as many decimal places as I can. Otherwise, I'm going to introduce rounding error. If you have a calculator that can store values, this would be a wonderful thing to store in your calculator to be recalled later. If you've got a question about storing objects in your calculator, please come talk to me and I'll show you how to store values in your calculator for easier and more accurate calculations. Now, there's another thing you can do as well. I'll go ahead and just bring this up. You can take this final velocity now. I know, right, this is 16.73 right here, meters per second. And you can set up a relationship here with the area of this trapezoid. It'll have time in it. And now that you know both velocity points and you know that your displacement here is 30 meters, you can actually use this graphical representation to solve for time as well. For the sake of time, I won't go through that, but I would like you to try that and see if you get the same answer. Now, coming back down here, I'll go ahead and, again, plug VF into equation 3. And again, I'm labeling and describing what I'm doing. So that would be VF equals VI plus AT, and rearranging for T, that would be T is VF minus VI divided by acceleration. And then if I go ahead and plug in my values, that would be T is 16.73 minus 10, and that would be all over 3, meaning that my time would be 2.24 seconds. And I actually did use the full value when I plugged this in, so I did not plug in 16.73, I used the full calculator value. So again, just be mindful of that. So there's my time. Last thing you'll do is evaluate your answer. Very, very important part of the process. The sign, it's positive, right? Good. Time should always be positive. So time is always going to be a positive value. And I did get a positive value, so that's a good sign. My magnitude, let's see, 2 seconds is a reasonable amount of time, I would say, for an object to travel 30 meters. There we go. So we're just checking to see if our answer makes sense. If I got 2,000 seconds, I might be a little bit off. I may have a unit conversion or something in there that's off. And then my units, what I'll do is actually just check my work here. So I'll say the square root of meters per second squared plus meters per second squared times a meter. Hopefully you see what I'm doing here. I'm going back in and taking a look at how my units worked out throughout my entire problem solving process. Well, this would give me the square root of meters squared over second squared plus meters squared over second squared, which would just be meters per second. That's good. That was the speed or velocity. And then if I were to look at this one, right, the time calculation, that would be meters per second minus meters per second over meters per second squared, which would give me meters per second times second squared over a meter. Whenever you divide by something, you actually multiply by the reciprocal. So saying over meters per second squared is actually the same thing as saying times second squared over a meter. So then my meters would cancel, my second would cancel with the second squared, and I get seconds. There we go. Beautiful. Okay, now this may be a lot of work, and you may be going, do I really have to do this for every problem? For right now, while you're learning how to solve problems, it's incredibly important to master this process and understand deeply what you're doing. So I will ask you to use this problem-solving template for the problems in the kinematics exercise document. So please grab as many of these handouts as you need, and please use this process every single step. I will assess you on your ability to use this process, and you will be given points for each part of the process. So please know your final answer is not the only important thing. Your thought process and your work are just as important. Thank you.